Green Chemistry Award for Small Business in 1996. Donlar has applied polyaspartate technology to everything, from sustainable agriculture to diaper manufacture. Company founder Larry Koskin had a vision that if shellfish could produce a natural polymer that prevents scaling and also biodegrades, perhaps we could too.
I came across an article that talked about two marine biologists who discovered that as a seashell grows, the animal itself secretes a series of biopolymers. Within this series of biopolymers was a very large polyaspartic acid. As soon as I read the article, I had this chill that just ran up and down my spine. And I knew that these guys had discovered what appeared to be a natural replacement for the current polyacrylates that are being sold today. Donlar was actually formed on January 8, 1990. And a half later, we had our first patent on the production of polyaspartic acid. And as far as I know, it's the first patent on a large-scale production of a protein.
The disposable diapers, as we know them today, really began to take off at about 1980. So we've had about 20 years of experience with these diapers. The problem with diapers is that they don't go away. We're producing about 20 billion pounds a year of diapers, and every year they sit right where they put them, in landfills and places like that. A component of superabsorbents is polyacrylate. Polyacrylates do not degrade. They persist in the environment. The superabsorbent that we're making today is as good as the current commercially available superabsorbents.
This facility is our Process and Technology Center. In this center, we not only manufacture our products, but this center also houses our pilot plant operations. So all of our scale-up and engineering activities are done at this site. Because the process itself in producing polyaspartic acid is a benign process, the only byproduct that's produced from all the chemistries is water. As a result of that, we have no need for waste treatment. As far as I know, this is one of the few plants, if not the only plant in the United States, that does not have a waste treatment site.
Fertilizers in the United States are a $10 billion input into growing crops. And nearly half of that goes into the corn crop alone, which is largely in the Midwest. No more than half of the fertilizer that's applied, of that $10 billion input, is taken up by the crop. What Amizorb does with nutrients in the soil is acts as a magnet, is a very strong collector of nutrients to hold them in place for more efficient uptake by the plant. The plants more aggressively can take up a constant supply of food, which results in improved yields and significantly improved quality traits to the plant itself. Amizorb is important because it's providing an entirely new platform of technology for crop inputs, including crop nutrition, protection, and seed coating technologies.
It's the chemistry of the polymer and how you can build these properties into it that will allow these materials to be used in a wide assortment of markets, even markets that I'm not even aware of today. But I'm very certain that this technology will find its way in just about everything that we do.
University-based research is an important component for green chemistry development. In particular, universities can engage in the longer-term strategic research that is often more difficult in industry. They can also provide an educational opportunity for incorporating green chemistry into the training of chemists. Terry Collins and his team at Carnegie Mellon won the Presidential Green Chemistry University Award for their work in developing environmentally friendly catalysts that fight persistent pollutants.
I have been in a course called Introduction to Green Chemistry and have done it nearly every year since 1992. The flows of matter to and from the ecosphere will define our ability to survive with a high level of civilization on this planet. We have a large amount of evidence the flows of matter both in and out of the human economy from the ecosphere are building up against us in very unfavourable ways. Unless we begin to address these things, we're going to be running into acute and chronic problems that will undermine civilization. My research group generally has 7 or 8 graduate students. There are several more senior people, research faculty members, and also we involve undergraduates in research a great deal. We develop these catalysts that have very long lifetimes for activating hydrogen peroxide in water. They're easy to make. Use them in very minute quantities. They work over a fairly broad pH range and tend to be very useful for a large number of applications. In the pulp and paper area, we have the most selective totally chlorine-free technology for bleaching wood pulp. Wood pulp is produced at about $50 billion worth per year. The pulp and paper industry is an enormous industry. It spends $7.5 billion in its bleach plants every year. However, we do not yet have a totally chlorine-free technology that can be used to produce very high-quality papers across the board. I personally believe that catalysts are going to deliver this. Our catalysts bleach wood pulp much faster than really any technology. They speed up the reactions of hydrogen peroxide for bleaching wood pulp dramatically. And they're used again in very, very small quantities in that process. In laundry applications, they're very good dye transfer inhibition agents. The environmental benefit of that is that it will allow people to do their washing with vastly less water. The most important application that I can conceive of for our catalysts has not been realized. It's the application that led us into this area of research in the first place, and that is to learn how to disinfect water with hydrogen peroxide rather than using elemental chlorine or very energy-intensive